Okay, so you should see question number 13 at the top of your screen. Can everybody see that? Question number 30. Perfect, perfect. Okay, well, let's start with question number 30. It asks us to circle the molecule that would be expected to have the lowest boiling point and explain why that would be. Well, let's start by drawing them all out. So we have 3 pentanone. So we have 1, 2, 3, 4, 5 carbons. On the 3rd carbon, we'll have a ketone. So that's 3 pentanone. Then it asks us to draw 1 ethoxypropane. So we'll start with 1, 2, 3 carbons like that, and then we'll put an ethoxy on it like this. Remember to count your carbons carefully, right? We have 1, 2, 3, right? And then we have our ethoxy group here. So that's 1 ethoxypropane. Okay, next we have pentanal. Pentanal is an aldehyde, right? We know that because of the suffix al. So we have 1, 2, 3, 4, 5 carbons in pentanal. And then finally we have 1 pentanol. So 1, 2, 3, 4, 5. And then we'll put a hydroxyl here. Well, if we look at the functional groups in these molecules and we evaluate them, in terms of the strengths of the intermolecular forces, since we're looking for the molecule at the lowest boiling point, we're going to look for the molecule that has the weakest intermolecular forces. Now, if I look at 1 pentanol, its major intermolecular force will be hydrogen bonding. It also has dipole-dipole forces and London forces, but hydrogen bonding will be the strongest one of those 3. Pentanal is going to have dipole forces, okay, as will 1 ethoxypropane. So we'll put dipole here as well, dipole. And then in 3 pentanone, that also has dipole forces. Now, if we're looking for the lowest boiling point, we know that intermolecular forces go hydrogen bonding is the king of the castle, right? That's going to be stronger than a dipole force, and that's going to be stronger than a London force. So then we look at our possible answers, and you see that we have 3 molecules that have dipole forces. Well, this is something that we went over in class several times where we said, okay, if I look at the dipole in a molecule like pentanal or in 3 pentanone, it has, those molecules are called carbonyl compounds, an aldehyde or a ketone, and they have a strong dipole. Yes, there is a dipole in the ether, 1 ethoxypropane, but it is a weak dipole. So we'll put here weak dipole. And so since the dipole is weak in an ether compared to that in a ketone or aldehyde, the answer is going to be 1 ethoxypropane is going to have the lowest boiling point. All right, let's take a look at number 31. It asks us which of the following compounds will undergo oxidation using potassium dichromate to form a carboxylic acid. So potassium dichromate, that's K2Cr2O7. It's just an oxidizing agent. Well, in A, we have a ketone. In B, we have an aldehyde. And in C, we also have a ketone. Now, the reason why you can't oxidize A or C is because this carbon, okay, with the carbonyl attached to it, it doesn't have a hydrogen. Whereas the carbonyl in an aldehyde, it does have a hydrogen attached to it. And so we can oxidize an aldehyde further to a carboxylic acid, whereas a ketone cannot be further oxidized. Okay, and so the answer is going to be the aldehyde. So this molecule is called cyclohexane carbaldehyde. Okay, question number 32. We've already gone over this. It says, explain why a ketone cannot be oxidized to a carboxylic acid. If we draw a ketone like acetone, let's say, and if we try to oxidize that, we're going to get no reaction, right? And the reason why is because it doesn't have what's called an alpha hydrogen. So an alpha hydrogen means that it's going to be attached to this carbon that we call the alpha carbon. So no hydrogen. Whereas if we tried to oxidize, let's say, propanal, we'll draw, constitutional isomer of acetone. So propanal, if we try to do the same thing, if we try to oxidize that, we are going to oxidize it to a carboxylic acid, and the reason why is because it has an alpha hydrogen present. Okay, nothing more than that. Where was I? Present. All righty. Well, let's move on. Number 33. Can 2,4-dimethyl-3-pentanone undergo keto enol tautomerization? What's tautomerization? Tautomerization is simply isomerization by the movement of a double bond and the placement of a hydrogen. Nothing more than that. For example, if we look at acetone, okay? So this is acetone here, or propanone. It does have an enol form, so it doesn't exist very much, but it does have an enol form that looks like this, right? Again, what did we move? We moved one of the hydrogens here to here, and then we moved the double bond from here to here, right? This is what we call the keto form, and this is called the enol form. Now let's draw this molecule, 2,4-dimethyl-3-pentanone. So let's start with drawing 3-pentanone. So there's 3-pentanone, and if we put 2,4-dimethyl. Well, in order for it to be able to undergo keto enol tautomerization, I have to have a hydrogen here or here. And we know that there's two hydrogens there, right? There's one hydrogen on each side. And so the answer is yes, this compound can undergo keto enol tautomerization. And we'll just do it. Why don't we just choose this side right here? We'll move that double bond and that hydrogen. And what we would end up with is something that looks like this, where we have our alcohol. There we go. So this would be our enol form, and this would be our keto form, like that. Okay, question 34. Write the product or products of the reaction below. What is the name of this reaction type? We're starting out with an alkene. So we're starting with an alkene, and we're treating it with hydrogen and platinum as a catalyst. This is called hydrogenation. Hydrogenation. Okay. I'd say it's one of the easier reactions that we look at. Notice I didn't say it was easy. I said it was easier compared to some of the other reactions that we look at. But if you look at these carbons here, right? This carbon has a hydrogen attached to it. This carbon at the top has no hydrogens attached to it. What are we going to do? We're going to take a hydrogen and add one hydrogen to this carbon, and we're going to add a hydrogen to that carbon. So we're going to take the alkene and we're going to convert it to an alkane. Now, if I just draw the bond line structure, which is the way I like to do it, it's a lot faster. All you would do is end up with that. And if you're like Mr. Deon, all you did was erase the pi bond. That's right. That's all you have to do, right? Hydrogenation is just a way of saturating the carbons on a double bond. Nothing more than that. Okay, let's move on from there. Draw the bond line structure of 2-methylpropyl butanoate. Okay, so if we see 08 at the end, that's a key that this is an ester. So our molecule must have this kind of functionality in it. Now, the first part of the molecule, 2-methylpropyl, that comes from the alcohol portion. Okay, so that's going to be on this side, and the butanoate, that's going to be on this side of the molecule. All right, and if it's butanoate, that tells us that it's got 4 carbons. So we could add our 4 carbons. We got 1, 2, 3, 4. So now we've taken care of the 2-butanoate. Now we need 2-methylpropyl. So we'll start with a propyl. 1, 2, 3, like that. And on the 1, 2, so on the second carbon, we will put a methyl group, and there you have it. Done. That's 2-methylpropyl butanoate. There's another name for this compound. There's also a common name for this compound. Okay, since this, can anybody recognize that alkyl group that I just circled? Maybe I'll circle it with the highlighter. Does anybody recognize that group? Just curious. You should.
Is that isopropyl?
You're close. It's an isobutyl. Okay.
Oh.
So it's an isobutyl. Yeah, it's got a total of 4 carbons, right? You're right. This part looks like an isopropyl, doesn't it? But we have a total of 1, 2, 3, 4 carbons in the whole thing. And so that is actually an isobutyl. So this could also be called isobutyl butanoate. Butanoate, like that. Okay, next, name the following molecules. Just some good old nomenclature problems. Students are usually pretty solid on these. So the first one's a carboxylic acid. Let's count the number of carbons in the longest chain, which hopefully you can see is not So 1, 2, 3, 4. No, that's not the longest chain. The longest chain is 1, 2, 3, 4, 5. And so we have 2-ethyl pentanoic acid, right? Pentanoic acid. Now that would be the systematic name, wouldn't it? That would be systematic name, okay? We'll leave it like that. If I wanted to come up with a common name for that molecule, and you should be able to do that as well, remember for that we use alpha, beta, gamma, and delta, right? So this would be alpha ethyl, valeric acid. Valeric acid. So this is the common name. All right. Well, let's look at the next one. This one, I think it's easy to find the longest carbon chain here. We'd have 1, 2, 3, 4, 5, 6. All right, 6 carbons in the chain, like that. And we want to number it such that we give the first substituent the lowest possible number, right? First point of difference. Remember that a halogen doesn't have any priority over an alkyl group. So we have a bromo, an iodo, and a methyl. And since they don't take any special precedence, we're going to number this right, 1, 2. Because if we went in the other direction, we'd have 1, 2. Sorry, I guess I should have kept going. We'd have 1, 2, 3, right? So we'd have a 2 and a 3. Whereas if we went in this direction, 1, 2, 3, 4. So the 2 is the tiebreaker going from the other way. Okay, so let's number it off. 1, 2, 3, 4, 6, like this. So this is some kind of hexane. We've got a 2-bromo. If you need to, you can write a little laundry list here. 2-bromo, 3 iodo, and a 5-methyl. And then it might be easier to alphabetize them. So B comes before I, and I comes before M. And so this molecule would become 2-bromo, 3 iodo, 5-methylhexane. Methyl. Kind of running a space here, so I'll just write it here. It's not hyphenated. There's no space. Methylhexane is all one word, but that is the final answer, all right? Okay, so 2-bromo, 3 iodo, 5-methylhexane. Okay, and over here we came up with a systematic name and a common name for a carboxylic acid. And remember, you should know the common names for the first 5 carboxylic acids and the first 5 aldehydes. We went over those in a lot of detail in the class. Okay, next it says, draw the line angle formula of hexadecanoic acid. Look, this line angle, like I told you last lecture, is the same thing as saying a bond line. But this one's kind of a funny one because we didn't go over compounds that have more than 10 carbons in them a whole heck of a lot. They did come up, of course. But if you see decanoic acid, you can probably guess that that's got 10 carbons in it, right? And if you see hexa, you can probably guess that you tack 16 or 6 carbons on that, so that you get a total of 16 carbons like that. So let's draw it out. This is a fatty acid. So we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. That's it. Nothing more to it than that. So this is just practice drawing a fatty acid. And you know, there's some questions like this that are in the textbook. And I think the reason that she puts them in there is she wants to make sure that you realize that this is a carbon or that you don't skip that one or something and put it in extra something. Anyhow, which would you expect to have a higher melting temperature, decanoic acid or cis-dec-6-enoic acid? Let's start by drawing them out. Okay, and you don't even have to do this to solve the problem. Decanoic acid, so that's going to look like this. What do we got here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? And then if we draw the cis, that means they're on the same side, dec-6-enoic acid. And this is a bifunctional compound, right? It's got 2 functional groups. It has an alkene in it, and it has a carboxylic acid. Let me show you how to do it. Look, you see that you have a decanoic acid, okay? But at carbon 6, you have En, En. So that means there's a double bond at carbon 6, and it's a cis double bond. Look, so let's try it here. So we got 1, 2, 3, 4, 5, 6. And then it's going to look like this. Okay? Maybe I could draw it like this. This. Okay, look, I have 1, 2, 3, 4, 5, 6. So since it's cis, 7, 8, 9, 10. Yeah, that's probably easier way to draw it. Okay, so now I want to compare these two carboxylic acids. Does anybody have a guess as to which one is going to have a higher melting temperature? The one in red or the one in blue?
I would guess the one in red because it packs more efficiently.
Oh, absolutely. Couldn't have said it better myself. So did I skip ahead like a million slides? Probably. Anyhow, here we go. Yes, why don't we just write it? So we'll say higher melting temperature due to more efficient packing. Yeah. Efficient packing and more effective IMFs, because they both have London forces, right? And they both have some little bit of hydrogen bonding here, which is negated mostly by the size of these chains. But either way, it's going to have more efficient packing. In fact, we talked about how unsaturated fatty acids are usually found in things like oils, right? Canola oil or olive oil. Whereas a saturated fat like that, those are found in animal fats like tallow and beef fat. Sorry, tallow is beef fat, like butter, for example. Anyhow, all right. Oh, here we go. Here we go. Number 39. This is an important question. Draw the products of the acid hydrolysis of 2-methylpropyl ethanoate. Right? Ester hydrolysis. So it says acid hydrolysis, but it's the hydrolysis of an ester, OH, in acid, right? I told you ester hydrolysis in acid is extremely important in this class, as is ester hydrolysis in base. So let's start by drawing the compound, 2-methylpropyl ethanoate. Now, we already drew a 2-methylpropyl earlier tonight, so I won't spend a lot of time on that. We have our 2, here's our 1, 2, 3, there's our 2-methylpropyl. If it's an ethanoate, that means it's got 1, 2 carbons like that. So you could also call this compound isobutyl acetate. So isobutyl acetate would be the common name of that ester. Anyhow, we're going to take that ester and we're going to put it in acid and we're going to heat it up. All right, what are we going to do? We're going to break the carbon-oxygen single bond because it's a lot weaker than the carbon-oxygen double bond. Then what are we going to be left over with? We're going to be left over with this part and this part. And since we're adding what? We're adding H2O, right? We're lysing it and we're breaking it with H2O. So we're going to put OH here to make acetic acid, and we're going to put a hydrogen there to make isobutyl alcohol. There you go. That's it. So that's acid hydrolysis. So hydrolysis of an ester in acid. Very important in this class. Okay, draw the products of the base hydrolysis. Does anybody remember the SATC name that we use for base hydrolysis of an ester, butyl acetate? I'll start by drawing butyl acetate. Darn right, saponification. Thank you. So Johnny and everybody, yeah, perfect. Saponification. Couldn't have said it better myself. So butyl acetate, 1, 2, 3, 4. Right here's my butyl, and then this part here is my acetate. Okay, not butyl. Okay, so there's butyl acetate, and we're going to do the base hydrolysis. So we're just going to put it in hydroxide, and we're going to heat that up. What are we going to do? We're going to break the carbon-oxygen single bond because it's much weaker than a carbon-oxygen double bond, isn't it? Then what are we going to be left over with? We're going to be left over with this plus this part here. 1, 2, 3, 4. Okay, we're adding hydroxide, OH minus. Maybe I should have color-coded that, the OH minus. Here we go. So I've got OH minus. I'm going to put the hydrogen here to make the alcohol, but I'm not going to make an acid if I'm in a strong base, am I? I'm going to make a carboxylate. And there you have it. This is called saponification, right? Hydrolysis of an ester. Yes, go ahead.
So if that was like potassium hydroxide instead of just hydroxide, would we be making a carboxylic acid salt in that case?
Absolutely. In fact, okay. That's probably what's going on here, right? Because you can't reach in the shelf and just grab a bottle of hydroxide. It doesn't exist, right? But as you've seen throughout the course of this class, chemists love to leave spectator ions out, right? The potassium is a spectator ion. And you might remember from Chemistry 101 that you learned about molecular equations, ionic equations, and net ionic equations. Well, organic chemists can't make up their minds, okay? You know, sometimes we like to include spectator ions, like I have written here in green, but I'll be honest, organic chemists are usually lazy, and we just leave them out. Okay, but your point is totally correct. All right, next is just a little bit of nothing more than a little bit of nomenclature practice and drawings of cis 1,2-diethyl cyclopentane. So look, our parent is cyclopentane. So we could start by drawing that out. Cyclopentane, so that's a 5-membered ring. On carbons 1 and 2, we've got cis 1,2-diethyl. So we'll put cis like this, and then we have 1, 2, and 1, 2. There you have it. Next one, this one's kind of a hard one. Okay, I would never ask this on an exam to draw something that, it's not that it's loony or anything, it's just tough, right? 5-bromo 3 isopropyl trans 2 hexene 2 thiol. Well, you got hex 2 ene and it's trans. So we got 1, 2, 3, 4, 5, 6 carbons like that. And on the second carbon, we have a double bond like this. On the second carbon, we have a thiol. That's going to go here like this. On the third carbon, we've got an isopropyl. That's going to look like this. Oh, shoot, where are we? So look, 1, 2, 3, 4, 5. And on the fifth carbon, we've got what, a bromo? Okay, I'm not a major fan of this question, but I'll blame it on my buddy that helped me come up with this review. Next, we got 2-methylpropyl, 2-chloropropyl ether. This one, I think, is a pretty legit problem, right? You got an ether, right? Everybody knows that an ether is an oxygen with 2 groups attached to it. So on one side, we've got a 2-methylpropyl. So look, we got 1, 2, 3. And on the second carbon, we got a methyl, and on the other side we got 2-chloropropyl. So look, we got 1, 2, 3, and on the second one we got a chlorine. Nothing more than that. Next one is practice drawing an amino acid. You got 4 amino, and when you have amino, that's just adding an NH2. 5 hydroxy. When you have a hydroxy, that's just adding a hydroxyl, an OH, and octanoic acid. So look, everybody who's hearing the sound of my voice can draw octanoic acid with their eyes closed, right? So you have 1, 2, 3, 4, 5, 6, 7, 8, okay? On the fourth carbon, so if we write 1, 2, 3, 4, 5, 6, 7, 8, okay? On the fourth carbon, we're going to put an amino group like that, and on the fifth carbon, we're going to put a hydroxy, and that's it. Okay, nothing more than that. Number 41, industrially, we often need ethanoic acid. Remember, ethanoic acid is the same thing as acetic acid, a 2-carbon carboxylic acid, right? This is acetic acid. Okay. The starting material for this product is usually ethylene, or ethene, which is this. Show below a series of reactions that would transform ethene to ethanoic acid. Look, this is another thing I wouldn't ask you, but I think. But I still think it's worth discussing. So again, I will never ask you this, but yeah, the way I have one way written out in my oh, sorry, I have something different written in my solutions guide here. Look, the way you would simply do this is you would add acid to this, and then it would do a Markovnikov addition, okay, which isn't important because this alkene is symmetric. Look, then you'd end up with ethanol, and then all you'd have to do is oxidize it. Okay, that's all really it's talking about. So I'm not a major fan of this question, but again, so don't turn me off because the point is still important, right? You're just doing addition of water in the first step. So this is addition of water across the double bond, and then this step is nothing more than oxidation. Okay, so it's got nothing to do with hydrogenation at all. Okay, if you were to hydrogenate ethylene, right, if you were to do a hydrogenation reaction on that, you just get ethane. Next is a question that everybody knows the answer to, so we'll just kind of go quick here. What is saponification? We'll put here the base base hydrolysis, base catalyzed hydrolysis, and ester. What type of biological molecules includes many hemiacetals? Hey, I'm going to ask my students, does anybody know? No, it's not a triglyceride. It's a carbohydrate. Yeah, if you don't remember, let me show you. Okay, so first let's go over what a hemiacetal is, right? If you have a carbon and it's got an ether and a hydroxyl, okay, and the other groups could be hydrogens, doesn't matter. You could have a hydrogen, two hydrogen, right? These could be R groups, not important, okay? But you've got a hydroxyl and an ether on the same carbon. Well, where do we see that? We see that in a molecule, like let's say you have, you know, alpha D glucose, right? If we identify, this is on there. There we go. If we identify the hemiacetal here, it's on the anomeric carbon, right? You have an ether attached here, and you have an alcohol on that anomeric carbon. This is a hemiacetal, and so the answer is carbohydrates. All right. Keep tracking here. Name the following molecules. I don't know. Some of these are great. Just kind of food for thought here. Let's see here. Did you notice that no, I guess the order's correct. 43, 44. Okay, the first one, the parent, it's got 5 carbons. It's a ketone. So this is a cyclopentanone, and we've got 1, 2, 3. We've got a methyl in the 3rd position. So this would be 3-methyl cyclopentanone. The next one is some kind of cyclobutane. If you number it 1, 2, 3, it's a 1,3-dibromo cyclobutane. And if we add one other thing to that, both of these bromines are on the same side of the ring. And so this would be cis 1,3-dibromo cyclobutane. The next one is an ester. It's a derivative of formic acid, right? This would come from formic acid, or you could even circle this whole thing and say that comes from formic acid. And here, this would come from ethanol, right? This part would come from ethanol. So we've got ethyl formate. Ethyl formate. Now that would be the common name. The systematic name would be ethyl methanoate. Okay, let's go down here. Hey, I have a question for you guys. Can anybody name this compound right here if I circle it? This compound, it's a compound that we looked at a bunch of times. You're darn right. It's some kind of anhydride. You're getting closer. Okay, so hopefully you remember that this compound was made if you take 2 molecules of acetic anhydride, right, and you heat them up high enough so that you lose water, right? You lose H2O. You end up with, that very molecule. Okay, this is called acetic anhydride, and we only ever looked at the common name of that compound. So there's the synthesis of acetic anhydride. Hey, there's some chestnuts in here. Does anybody recognize this compound here? If I circle it in red, could anybody tell me what the common name of this is? One of those compounds that you did have to memorize the common name. Anyone? No? What I have circled in red. Does anybody remember anisole? Anisole, right? There's a benzene ring with a methoxy group on it. Okay, anyhow, that's what that is. That's anisole. And so this would be our first carbon. 1, 2, 3, 4, 5, 6. And so this would be 2,6-diethyl anisole. And the last one is an amide. Okay, and we've got 2 methyl groups on here, so this must be some kind of NN dimethyl right? And then if we've got 3 carbons here, this would be propanamide. Propanamide. That would be the systematic name. It's also got a common name. I'm going to blow your mind here. Okay, so this is the systematic name. The common name for this molecule would be NN dimethyl propionamide. Okay, so that would be common. All right, let's see here. Number 45 just asks us to draw the Lewis structure of each of the following functional groups. So if we draw an alcohol, we're going to have OH, so oxygen has 2 bonds, 2 lone pairs. We draw an aldehyde, we're going to have a carbon with a double bond to oxygen. Oxygen always has 2 bonds, 2 lone pairs, and we have a hydrogen attached. A carboxylic acid, got a double bond to oxygen. We have another oxygen with 2 lone pairs, right? But they're 2 single bonds, and we have another R group. And then an alkene is just where we have, you know, a carbon with a double bond. All these R1, R2, R3, R4, like that. Alkene. Okay. Let's see. A little more practice. This is right back to where we started tonight, which is questions 46 and 47 go together. Okay. If we look
Mr. Deon?
Yeah, go ahead.
Sorry, the previous question for carboxylic acid, the structure.
Did I draw an ester? Johnny, I was testing you. Good job. Yep, there we go. Mr. Deon's got to lay off the wine. It's the supper table, I guess. Okay, yeah, carboxylic acid. Yeah, I drawn an ester, hadn't I? Yeah, esters on the brain. Okay, let's try the next one. There's a lot of work in this one. It's asking us to name all 4 of these molecules over here. So we'll start with this one in the top corner here. That's an ester, right, Johnny? It's ethyl acetate here. So we have ethyl acetate or ethyl ethanoate. I'll just leave it like that. This one here is diethyl ether, right? It's an ether with 2 ethyl groups. So this is diethyl ether, which does have a common name, which is simply ethyl ether, but we'll leave it at diethyl ether. Let's see here. Over here, we have an alcohol. So this is isopropanol, right? You have 1, 2, 3 carbons, and you have the hydroxyl on the second carbon. So this is isopropyl alcohol, or you can call it 2-propanol. Either one is fine. 2-propanol, which is isopropanol. What's next? Next we have a ketone. So it is, this one here is 2-butanone. 1, 2, 3, 4, yeah. So this is, or just butanone. Butanone, like that. Okay, so we have all of them. So that means we've got an ester, an ether, an alcohol, and a ketone. Well, we know that alcohol is going to be number 1 on the list, right? Because it's got hydrogen bonding. Now, between the ester and the ketone, right? The ester and the ketone. I never taught you how to differentiate between those two, you know, to discern which one would be higher than the other. In fact, it's very difficult to predict, really. So you could put 2, 3 here, and you could put 2, 3 here, right? The ether is going to be the highest boiling point, or the lowest boiling point for sure, right? It's got the weakest dipole in it. Just to kind of point out how you can't discern between the boiling point of an ester and a ketone, I actually wrote them down. The boiling point of this ester is 77.1 degrees Celsius, and the boiling point of butanone is 79.6 degrees Celsius, right? They're very close. The boiling point of isopropanol is 82.5, so it's a little bit higher, and the boiling point of the ether is really low. It's 35 degrees Celsius. And so again, it's really hard to tell the difference between those two, and I wouldn't expect you to be able to differentiate between the boiling points of the two. Okay, number 48, something that we already did. We already looked at keto enol tautomerization. Let's say, for example, we look at butanone, which was on the last line, right? We know the keto form is going to predominate. And then if we draw the enol form, it would look something like this. This is the enol form. Do you assume the double bond because there's no hydrogen bonds on the carbon just before the oxygen? Can you remind me which question you're talking about there, Greg? Sorry, I didn't see your question until I looked up.
I was talking about the one with butanone.
The butanone. Do you assume the double bond because there's no hydrogen bonds on the carbon just before the oxygen? Yes, absolutely, yeah. So when you look at this structure here, whenever you see a carbon and an oxygen next to each other in a formula like that, yeah, it's got to be a carbonyl, right? Because think about it. The carbon has to have 4 bonds. It's bonded to this carbon, and it's bonded to that carbon. That's only 2 bonds, right? So that means it must have a double bond to the oxygen.
Yeah, that makes sense. I just thought I had remembered illustrating double bonds in the condensed structure. So
no, it's a great question, right? You have CH3, then you have a carbon. Let's just ignore this oxygen, right? Then you've got CH2, CH3, right? Carbon's got to have 4 bonds, so it means that bond to the oxygen must be a double. Yeah, yeah. You know, something else I want to show you guys about this one here is, remember when I told you about tautomerization this evening? I said, oh, you've got to have a proton on the carbon next door. Well, you could also have, so that's an enol form, but you could also tautomerize with this proton as well. And that would give you this enol. Okay, so this is also an enol, and they're both legit. So I have a tough question for you. Which enol do you think would predominate? The one I circled in blue or the one I circled in green? Because one of them would predominate in solution. And it's not a trick. No tricks. Okay, the answer would be the one in blue. All right, it would predominate because it's more substituted. Right? This carbon is attached to an oxygen, a carbon. This carbon is attached to a carbon and a hydrogen. Right? So overall, it's got oxygen, carbon, carbon. Right? The hydrogens don't count. They're like nothing. Whereas if I look at this one here, it's attached to oxygen, carbon, and 2 hydrogens. Okay, so since this one is more substituted, it would predominate. Yes, go ahead.
Isn't that like a Zaitsev's principle?
No, that's something completely different. Okay, so Zaitsev has nothing to do with an enol whatsoever. Okay, Zaitsev would mean if you were taking, let's say, 2-butanol, right, and you were heating that in acid, okay, and you eliminate water, right, minus H2O, right, and in that case, you could either pull off the alpha proton here in order to make 2-butene, or you could pull off a proton here to make 1-butene, right? That's what Zaitsev product is all about, right? This would be a Zaitsev product.
So in that case, 2-butene would be more substituted.
Absolutely.
And that's why it's Zaitsev's product.
Yeah. But I just don't want you, substitution, right? Talking about substitution is the same, okay? But don't mix up, there's no such thing as an enol in a Zaitsev product, right? So when you look at the relative stability of alkenes, right? Think about it. We did a whole chapter on alkenes. The simplest possible alkene you can have is ethylene, where it's attached, the carbons are only attached to hydrogens. It is the most unstable alkene you can have. Right? As soon as you start adding a carbon, so if you have a carbon like this, it's going to be more stable. If you add 2 carbons, you've got 2 possibilities, right? You can have them on the same side, right? Like that, or you could have them like this, okay? And you could have them, shit, I'm running out of space here, pardon my language, right? You could have them like this. Okay, everything that I have here, these are all di-substituted alkenes, right? Then you go to a tri, and then you go to a tetra. So the stability increases as you go in that direction, right? I ran out of space, but a tri-substituted would look like this, right? There's only one possibility. And then a tetra, right? A tetra would look like this, where everything is in our group attached to it. Okay, the more substituents you have, the more stable the alkene is. Nothing more than that. Okay, There we go. Okay, draw some structures. Just a little more nomenclature here. So we're asked to draw all these different molecules. 3-ethyl, 5-cyclopropyl, 2-pentanol. Let's start with the parent, which is 2-pentanol. So let's try it. We got 5 carbons. 1, 2, 3, 4, 5. On the second one, we'll put our alcohol. On the third one, we have an ethyl group. And on the fifth one, we've got a cyclopropyl. That's it. 3-ethyl, 5-cyclopropyl, 2-pentanol. Next one asks us for cis. Methyl 3-heptene. Now, these are bifunctional compounds. I put these in here to try to challenge you a little bit. But if it's got a 3-heptene, right, this means it's an alkene. But if it ends in Al, this also means it's an aldehyde. All right, so if we draw heptanal, okay, so that means it's got 7 carbons. Look, got 1, 2, 3, 4, okay, and this is a cis bond, right? It's cis at the 3. So 1, 2, 3, 4, 5, 6, like that, okay? And then what else do we have? 6, 1, 2, 3, 4, 5, 6. This doesn't make sense. Oh, sorry. 1, 2, 3, 4, 5, 6, 7. There we go. And at the 6th carbon, we have a methyl group like that. Not my prettiest work, but still the right structure. What's next? Okay, what's next here? We've got 2,5,6 trimethyl, 2,5-heptadiene 4-one. Again, this is a bifunctional compound. So look, we've got heptadiene 4-one. So we've got 7 carbons with a ketone at carbon number 4. So look, 1, 2, 3, 4, 5, 6, 7. At carbon number 4, we've got a ketone. Then at carbons 2 and 5, so look, if we number them, 1, 2, 3, 4, 5, 6, 7. At carbons 2 and 5, we have enes, right? Dienes. So that means we've got a double bond here, and we've got a double bond here. Okay? Then at carbons 2, 5, and 6, we have methyls. So 2, 5, and 6, like that. Notice that cis and trans are unimportant here, right? Because if I examine both of these double bonds, and I'll delete some of the spinach here to kind of clear it up. If you examine both of those double bonds, this one and this one, cis and trans are irrelevant. Why are they irrelevant? Because this double bond has 2 methyl groups. Whenever you have 2 groups on 1 carbon of a double bond that are identical, cis and trans is irrelevant, right? You could say that all of this is cis to this one, but it's trans to this one. So there's no cis or trans. And the same thing is true here. I have a methyl group here and a methyl group here. And so cis and trans are irrelevant for both of those. All right, there we go. Last one is cis-cis, 6-bromo-2,4-hexadecanoic acid. So look, my parent here is hexanoic acid. And it's got a diene, so I've got 2 double bonds, one at carbon 2 and one at carbon 4. This one's kind of tough too. Look, you've got 1, 2, 3, 4, 5, 6 carbons. And I've got my carboxylic acid here. If I number the carbons, 1, 2, 3, 4, 5, 6. At carbon 2, I have a double bond. I'm already seeing a problem here because that's trans. So I'm going to have to take this thing and move it like this. And I will delete all this spinach here. Okay, so 2, 3, 4. Make another double bond to make that cis, right? So I've got 2 cis double bonds, 1, 2, 3, 4, 5. 2, 3, 4. Shit, I put it in the wrong place. 1, 2, 3, 4. Okay, now let's try it again. Like that. There we go. So 4, 5, 6. All right, like that. So that covers my 2 cis bonds. And at carbon 6, I have a bromine. So I'll tack that on there. And there you have it. Again, that's kind of a tough one. This is kind of challenging. That's why I gave you this handout a long time ago to get some practice. Here's one that I think is a little more reasonable. Draw the reaction of propanol with 2-propanol to create a hemiacetal. We spent a lot of time looking at aldehydes, right? So this is propanol or propionaldehyde. Okay, and we're going to react it with propanol. Okay, and we're going to make a hemiacetal. Remember that a hemiacetal, we've got a carbon with a hydroxyl, another one with an ether. And we're going to have 2 R groups like that. Okay, did I draw propanolic acid when I meant to draw propanol? Sounds like something I would do. There we go. That's more like it. Now, there are a whole plethora of ways that you can memorize how to draw a hemiacetal. One of the ways that I told you was to say, okay, well, you've got a dipole going this way, right? That's going to render this carbon really electropositive. The oxygen's electronegative. That's neither here nor there. But a pair of electrons from this oxygen on the alcohol is going to make a bond here. Okay, so this is showing the bond formed. And then carbon cannot have 5 bonds. We call that a Texas carbon. There's no such thing. Okay, so what we do is that we move pi bond up here like this. Okay, now let me draw what you'd end up with. Look, you'd have 1, 2, 3 carbons. Then you'd have your bond to this oxygen up here at the top. You've got your hydrogen. Okay, so this hydrogen that I just drew, that's this one right here. I just pointed it down. Okay, then you're going to be attached to your oxygen and then 1, 2, 3 carbons. So then the question becomes, you know, where does this hydrogen go? Right? Where did that hydrogen go? And the answer is you're going to put that hydrogen on the oxygen like that. And so this is your hemiacetal. And if you're like, where's the hemiacetal? Look, this carbon is attached to an ether here and an alcohol here. Okay? So there's my hemiacetal. All right. You've got to be able to draw that. Or you've got to be able to at least recognize it because the final exam is all multiple choice. Okay, let's see here. Question 51, why are carboxylic acids more acidic than alcohols? Well, if you look at a carboxylic acid, let's just choose acetic acid. Okay, we know that an acid is a proton donor, right? Something that can donate a hydrogen. So if we draw the equilibrium where we show the carboxylic acid donating a proton, here we go. It's going to look something like this. Whereas if we do the same thing with an alcohol, let's choose a 2-carbon alcohol, ethanol, and we draw the same equilibrium. Okay, you're going to be left over with this. There's a big difference in stability between the acetate and what's called the ethoxide, right? And if you're unsure as to why, you know, this equilibrium is going to lie much more to this side than it would over here, right? In this case, it's just going to lie a little bit to this side, and mostly it's going to be the starting material. Okay, we'll make a much bigger arrow there. The reason why is because this conjugate base is resonance stabilized. If you're like, what do you mean by resonance, Mr. Deon? Well, what I mean is that negative charge doesn't just exist on this one oxygen, right? It can also exist on this oxygen at the top. Oops, that's not a resonance arrow. This is a resonance arrow. There we go. So it can also exist up here. Okay? Something you got to keep in mind about electrons when you're studying chemistry is that electrons are very high energy. If they can move, they will. The electrons that are making this oxygen negative in ethoxide are just stuck there. They can't go anywhere. Whereas the electrons that on the acetate here, they can move, you know, from here to here. So they have more space to move around, and therefore they're more stabilized. And that renders acetic acid a better donator of a proton. So that's the answer. Okay, draw the enantiomer. Remember, an enantiomer is a mirror image, non-superimposable mirror image. Okay, now there's a couple of ways you could do that. You could either really try to stretch your brain and try to draw an actual reflection like this, and then you try to, do something like that. That's one way of doing it. You try to draw a mirror image like that. That's not the best way, though, is it? A better way to draw an enantiomer is anything that's a dash becomes a wedge, and anything that was a wedge becomes a dash, right? So this is a dash, this is a wedge, and all we're going to do to draw the enantiomer is we're just going to reverse those. Look, we'll go 1, 2, 3, 4, 5. Here we'll put a wedge to the OH, and here we'll put a dash to the hydrogen, and that, my friends, is the mirror image. Okay, that's the enantiomer. What requirements must a carbon atom have to be chiral? Carbon must be attached to, who can help me out?
4 different groups.
Four different what?
R groups.
Yeah, 4 different groups. Yeah, 4 different groups. Okay, doesn't have to be 4 different atoms, does it? Right? If I have this carbon and I have a methyl group here, I've got an ethyl group here, I've got an isopropyl group here, and I've got a propyl group down here. Okay, this carbon is chiral because even though it's attached to 1, 2, 3, 4 carbons, right? It's attached to 4 atoms that are identical, but it's attached to 4 different groups, and therefore it is a chiral carbon. Nothing more than that. Okay, this one might be kind of tough. I don't know. It's asking us, how many stereocenters are present in the following compound. In fact, I don't even like this question. This is pretty tough because, we don't really talk about cis and trans bonds being stereocenters. Okay, what you guys would probably recognize would be 1, 2, 3, like this. Okay, but these ones here are also considered. This is considered a stereocenter, and this is considered a stereocenter. So it's 1, 2, 3, 4, 5 stereocenters. Anyhow, I would say that's a tough question. I will not ask that question directly. But I would ask question 55. Which of the following pairs of stereoisomers are related as enantiomers? Did anybody do this one? Anybody able to nail this one down? Or is anybody able to solve it now and see some enantiomers here? Right, because we looked at the enantiomers Deonyl glyceraldehyde or Deonyl glucose. That was in one of our lab reports. Well,
Would it be B and D?
Sorry, which one's B and D? I'd say so. Yeah, B and D are enantiomers, right? You just flip this over here, flip this over here. Yes, those are enantiomers, right? And the same thing applies for A and C. A and C are enantiomers as well, right? All you have to do is flip this nitrogen to the other side and flip this hydroxyl to the other side. There you go. So those are enantiomers, right? Remember the enantiomers that we looked at in our lab was Deonyl glyceraldehyde, right? We drew this, okay, and we said this is D-glyceraldehyde. And then to draw L-glyceraldehyde, all we did was take that same structure, copy, pasted it, okay, and then all we have to do is delete a little bit of it, switch the hydrogen and the hydroxyl like that, and now we have L-glyceraldehyde, which is the enantiomer.
Mr. Deon?
Yeah.
Does this mean that like A and B or A and D would be diastereomers? Is that correct?
Absolutely,
okay.
Yes. So if you look at A and B, for example, right, they're the same at this stereocenter, but they're reversed at that one there. Okay, so stereocenters that are, or stereoisomers that are not enantiomers would be, these would be diastereomers, right? Another diastereomer to A would be D, right? Because it's the same here, but it's different here. Okay, so there are several diastereomeric relationships that you could make there, but absolutely your conclusion is 100% correct. Number 56, progesterone, which is present in humans as a single stereoisomer, has 6 stereocenters. Human progesterone has how many possible stereoisomers? The answer is this. Number of possible stereoisomers is equal to 2 to the power of n, where n is equal to the number of stereocenters. Now, you don't need a calculator for the exam, but it would be 2 to the power of 6. So 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64. There we go. So it would be 64 stereoisomers. Dextrorotatory compounds can rotate plane polarized light in which direction? Dextrorotatory means they rotate it to the right. Right? Levorotatory is to the left. So just a couple of terms you need to know. The drugs Prilosec and Nexium both contain the same active ingredient. Nexium contains a single enantiomer, but Prilosec is a racemic mixture. Which drug will be more effective if you receive a 20 milligram dose of each? How much more effective? You guys remember what a racemic mixture is?
Doesn't it have both enantiomers in it?
Absolutely. It's a 50.
So it's optically inactive, or is it optically inactive then?
Absolutely. It's a 50-50 mixture of 2 enantiomers. Of 2 enantiomers. Therefore, this is just adding on here, therefore optically inactive. Right? So think about Nexium has 1 enantiomer, okay? And Prilosec has, 0.5 of one and 0.5 of the other. If they're, if in the racemic mixture, if only one is the active ingredient, right? Nexium is going to be twice as effective, right? So Nexium will be 2 times more effective at the same amount of dose, right? If you were to take, let's say, for example, you took 10 grams of Nexium, that means you're going to get 10 grams of active ingredient. If you take 10 grams of Prilosec, you're only getting 5 grams of active ingredient. All right, how many different triose sugars exist? Well, if you think about a triose sugar, this is a tough question. There's three triose sugars. Let's skip this one. I would never ask a question like that in that way. Numbers. The answer is D-glyceraldehyde, L-glyceraldehyde, and dihydroxyacetone. We've got D and L, glyceraldehyde, and dihydroxyacetone, which is this. Okay. That, yeah, if you did that over the weekend or something and had to research it, yeah, that's totally reasonable. How many chiral carbons are present in the straight chain form of glucose? What about the cyclic ring form? So if we draw the straight chain form of glucose, we looked at this, Avogadro's number of times. So we have a hydroxyl here, here, and here. Then we fill out the rest. Like this, okay? Well, if we tally up the number of chiral centers, there's 1, 2, 3, 4 chiral carbons in the open chain form of glucose. But if I draw the ring form of glucose, which I already drew one time this evening, but I'll draw it again, okay? We got one here, and I'm just going to draw alpha D glucose just for the heck of it. just the first thing that came to mind here. Well, if you label all the chiral carbons here, you have one here, which is this one. You have one here, which is this one. You have one here, which is this one. Okay, we also have one right here. And then we also have one here. And so we have a total of 5 here. We have 4 here, and we have 5 over here. Okay, let's see here. The following structure alpha or beta D-glucose? Circle the features that determine its designation. This is alpha because OH at anomeric carbon. Anomeric carbon is pointing down. Of course, if it was pointing up, that would be the beta position. The 2 simplest sugars are glyceraldehyde. So glyceraldehyde is this guy. I'll draw D-glyceraldehyde since it's naturally occurring. And dihydroxyacetone, which I just drew, this compound. Okay, dihydroxyacetone does not rotate plane polarized light. Why not? The reason why is it has no chiral carbons. Right? So it's not going to rotate plane polarized light, whereas this is a chiral carbon. Number 63, a glycosidic bond occurs when a blank functional group of a sugar reacts with a blank functional group of another sugar. So for example, if you look at a disaccharide like maltose or lactose, they are formed by glycosidic bonds, and they're formed between the hydroxyl functional group on one sugar and the hydroxyl on another. Draw the reaction which results in trans fatty acids in processed foods. Oh yeah, trans fats. Where do trans fats come from? Well, if you remember, if we take a naturally occurring unsaturated fat, so let's just use 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, something like that. So say we've got 12 carbons here, right? Naturally occurring unsaturated fats are cis fats. And then if you treat them with hydrogenation conditions, okay, this wouldn't be the major product, but it can happen where you get, instead of hydrogenation at the double bond, you get an isomerization. Okay, so instead of having the cis double bond, you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8. So 1, 2, 3, 4, 5, 6, 7, 8. So here you go from cis to a trans. Okay, and that's where a trans fat comes from. Okay,